I have a feeling that computational chemistry is here to stay in the long run. I think we're always seeing a lot of productive results coming in that area, and it could only get stronger.
As a kid growing up in Mexico, Osvaldo Gutierrez dreamed of becoming a professional boxer. But after moving to the United States, he fell in love with science. Today, he's working at the forefront of catalysis and computational chemistry research and acting as a powerful role model for younger generations. To kick off Season 2 of Bringing Chemistry to Life, we speak with one of Chemical and Engineering News' 2020 Talented 12 about their work and trends in their field. I'm your host, Paolo Braiuca from Thermo Fisher Scientific. We began by asking Dr. Gutierrez about the start of his journey into chemistry and to the United States.
It started basically my pathway as an undocumented immigrant, like many other immigrants that come to this country. And in my case, my family was moving away from Mexico, and we landed in Sacramento, California. As soon as we crossed the border, my mentality was, I'm going to be the best that I can be in the United States. And that was to become a medical doctor, but not just a medical doctor. I want to become a neurosurgeon, because to me that seemed very complicated. It seemed to me that would be the ultimate kind of goal to achieve as the American dream. The reason why I decided to go into chemistry, it was in Sacramento City College. It was the first science course that I got a C on. I got a C on chemistry. And for me, it kind of pushed me. I was like, I think I could do this. I think I want to basically adapt and change my mentality, change my major, and I want to do chemistry as my major. So I was driven by the challenge. As part of trying to get into chemistry, I applied for many different chemistry research labs as an intern. But one responded, Ken Howe, which is very surprising to me at this moment, because at that time he had a very large group and he had no undergraduates. So it was kind of strange that he actually decided to take a chance on me. And he's the one that responded and said, yeah, when you arrive to UCLA, we can discuss it, and we go from there. So for me, that's how I got into computational chemistry research. And then for me, slowly, I was really trying to impress him so much that I decided to stay longer and try to get excited about the project. Two things happened. I during the process that I was applying to medical school, I realized that no medical school was going to accept me because of my undocumented status. So I needed to provide, basically, they said the only way that we could see this working is that if you come up with a bank account that has enough funds to support you throughout the whole medical career. I was like, my family does not have $200,000, $300,000 in their bank account. My dad was making $4.25 an hour. That there's no way that we had that money. But then I started thinking, wait a minute, so why not this other career? With the goal that maybe it could change later on if the immigration status changed. But I was like, I think that will still be considered a doctor. I will still be a doctor in the United States. So that's why I switched into chemical research or the PhD in that.
And very successfully indeed, I would say. You seem like a fearless researcher. You seem to be going in directions that are pretty challenging. What drives you? Where do you find inspiration?
I think we find inspiration simply by the needs of societal needs, and exciting projects at the same time. So oftentimes, an experimental chemist that we meet via another colleague or a conference, they said, you do computations, we have this problem, and I tend to get very excited about my projects. And then I tell my students, you know what, this will be a very cool project. It's not maybe using iron chemistry, but it's using this other copper, or is using this palladium and so on. But I think this is a very exciting project that it could perhaps change the way we think about chemistry. I think what makes our group unique right now, that I have owned this kind of identity, is that we're able to do both the computation and the experiments. In the experiments, we focus exclusively only doing iron chemistry, whether it's this iron cross-coupling reactions. Early on, we started doing CH oxidation, but eventually we found that the three coupling radical cross-couplings with iron were more successful, so we decided to pursue those projects, and we have a lot of exciting results that we hope to submit in the next couple weeks and whatnot. In the computational part, we're free to explore anything, whether it's the iron chemistry, palladium chemistry, ruthenium, and so on, and we're just driven by curiosity.
Do you think chemists in general give up too quickly in terms of trying to understand the fundamentals of what's happening in the reaction, and they just very pragmatically look at what products they can get out of it and they just live with that?
I think so. I think in general, a lot of, especially both in the computation experiments, we give up too quickly on certain projects, and it's up to the PI to the graduate students to say, what is the ultimate goal of this project? And again, it's to gain mechanistic understanding. If we focus on that aspect, then every experiment that you do to try to gain any mechanistic understanding, it will be helpful, and we include that on the paper, and it'll also be good training for yourself. I think we're so focused and we're so pressured to publish, get grants, and they want results. They want an end product. And the tenure clock is clicking and so on, that you're like, we have no time to characterize all those compounds. If it's going to take you 1 month to identify all those, that's not going to be practical. But for me, it is practical. For me, it's actually very useful. No, that's our role. We're a mechanistic chemistry group, and our role is to identify things, and that's our focus. Our focus is not, we're not a synthetic group. Our focus is not just to deliver methods and for one particular focus in experiment or in computation, but it's rather to provide mechanistic insight. So yes, you should go, and it's going to take you 1 month or 2 months, but you should go and identify all those products that you made, characterize every single product that you made. And then the next reaction, before you do the next screening, we'll see how the ligand not only changes the product that we want, but also the product distribution of all the other stuff that we don't want. And then we collaborate and do internally to do modeling on those reactions. So that's our mentality. And oftentimes, though, I have a postdoc. I have now 3 postdocs that are doing synthetic chemistry. And their mentality is more of, we're going to do screening, we're going to focus on this particular product. So I think they get frustrated, but I needed to instill that early on, that remember that you're here in this group to do mechanistic studies. So it's not just about getting this particular product. It's to get that product, and what other ones are you getting? And that could be very instructive in terms of designing new reactions. And I think now the community is really moving towards that kind of, they're starting to appreciate in terms of publications, mechanistic studies more in general, that is not always about, well, this method is not 99% anti-selective and is, you still have only 50% yields. I mean, some groups publish papers with 35% yields because they see that it's an innovative, the method is something unique that we never thought about. That maybe 25 years ago, that would be a no-go. Basically, if you have 25% of one product, you're not going to publish that result. But I think now the community, like you mentioned, is becoming more interdisciplinary and is becoming more accepting towards mechanistic studies, both in the computational and the experimental.
I'm interested in your thinking process. Are you excited by the intellectual challenge of getting the fundamental understanding, or are you excited about what this understanding, this fundamental understanding, can lead to in terms of real world applications? Is it more finding it out, or what can happen when you find out?
It's more about finding out what could happen after you find out, basically to validate. That's what's really exciting, that if we're going to go through all this trouble to identify all this many products on this particular reaction, and if we do all the computations that follow up on this project, maybe a year, we have one project that took us 3 years in computational time to kind of 3 years in using computational chemistry to try to understand. But that led us into a model that before we published, we started thinking, wait a minute, if we're really going to have faith on our own calculations, this was a non-collaborative project, then we should be able to start proposing reactions, or else how are we going to sell this? How is the community really going to believe that we're able to do both? If we can't even believe ourselves, this computation. So not only do they need to kind of correlate with experimental evidence, but we always look for, and I think it's really exciting for me and for the group, that if this is really true, the mechanistic pathway that this follows, then let's propose something that would not be the first thing that you will try in a synthetic lab and see if this reaction works. So for me, that potential that it has on doing the mechanistic studies, validating those, is very exciting to me.
And I think we need a little bit of innovation in the reaction designs. And if I look at the current landscape, and for instance, in the pharmaceutical industry, you see a lot of repeating patterns. And it is largely because of the extreme use or even abuse of a relatively low number of reactions that are actually very effective, right? Do you see the field evolving at all?
Yes, I think ultimately the way we see that we're going to change the pharmaceutical industry is that I don't think they will have a problem with adapting a new method. If it was scalable, if they could do it in a large scale, and if it's not going to be a trial and error method, right? That they see that it's very clear that, let's say we do a reaction in the kilogram scale, we're going to reproduce this reaction. Is it going to be selective or not? We could deal with the selectivity. But what if it doesn't work for this other particular substrate that we need to tune it? Then do we completely restart this whole process, or can we stick with this type of method and tune it? And that's what we're looking for. If you really want to tune it at that large scale, you have no time for trial and error. They really want, tell me what exactly I need to do to the ligand, to the catalyst, or to the substrate or the reagent. That is not going to be a trial and error. And that's when we're trying to sell ourselves. That is like, if we do all these mechanistic studies on the smaller scale, and we do all this computational studies, then we could pinpoint at, this reaction, if we just do this, this should be transferable to the large scale. Ultimately, I think they would not have a problem if the reaction in the small scale was transferable to a large scale. And in terms of industry, large scale applications. And in academia, we hardly ever have an opportunity to do a large scale reaction. So we have no idea. A lot of the graduate students have no idea can this reaction work if you try to make multiple kilograms of this? Besides, rather than saying, I'm going to run the reaction in milligram scale, is it really going to scale to that degree? At best, you do gram scale. And that's almost rare in some cases. Some labs can only do that. But the idea is that, let's say they do that in gram scale, and it doesn't work. And what you don't want at that moment is to do a screening again, because then that's going to be a very tedious process. Industry is going to lose faith in what we're doing again, and they're going to go back to the same old reactions that are very robust at that time. But if we do mechanistic study, we say, no, wait. I think we understand what we need to do at this system, because we did some mechanistic studies, some computational studies, and you need to just simply do this other change. And I think that will be more trustworthy, I guess, or more reliable in a way, or industry will be more accepting towards new methods if we're able to pinpoint at things that they should do at the large scale to make this reaction work. I just don't think that they want trial and error at the large scale, because then that will be very costly. So they go back to their traditional methods instead, even if they're more longer or slightly more expensive with the metals and so on.
You're absolutely right. I agree 100%. And groups like yours are gonna be key, right, in leading us to the next generation of chemical reactions, and which I can't wait for. And speaking about next generation of chemical reactions, among the different things that you study and you publish on, I was particularly interested and attracted by what you mentioned before. Is the radical carbon-carbon cross-coupling. To me, it's a beautiful innovation. It's a nice way to introduce sp3 carbon functionalities in molecules, right? Something that can't be that easily done with other methods. And can we go a little bit into that? Can you describe what you have done there? Can you tell us why this is important? What excites you over the field, etc.
Yeah, on that reaction you're talking about, we use iron, a very simple ligand, and we combine 3 components at the moment. Eventually, we want to combine more components. And in a very predictable manner, we know how they're going to combine or glue together. And I think that becomes crucial, like I said, with the potential applications later on. Can this method be something that industry could use? And the answer is yes, because the metals are very cheap. The ligands are very common. There's nothing special about the ligands. We're trying to design new ligands, but right now is very things that you could buy, so that there's nothing special about this one's here. But what I think that was kind of special is the mechanism that this reaction we think that is going through. And I think that's where we spent, basically, when I started my independent position, to understand the 2-component cross-coupling with iron, I basically spent all my funds that I had allocated for the whole 5 years on computational time on this particular project. And the reason we did that, and I'm glad that we did that, is because we want to really understand what are the potential alternative pathways that this reaction go, how viable they are. And from there, we're able to kind of come up with a model system that maybe it is true that that's the true mechanism or not. We can never prove a mechanism, but at least it gave us a model system that now we're able to quickly expand from 2 components to 3 components. Same thing as nickel has recently been doing. So we're now, with our conversations that we have with our nickel colleagues, and they're doing a lot of 3-component reactions, we're thinking, why can iron not do these reactions? And the answer is yes, iron could do those reactions as well. And I think it could do them a lot faster. So now all our reactions are done within 1 hour. So that's something that I use to attract graduate students. Like, you'll be done in 1 hour with this reaction. We don't have to wait 24 hours and include many different additives. This is no additives added. It's just very simple. 3 components: the iron, the catalyst, and the reaction goes sometimes in the absence of solvent. So you use one of your components as solvent. So that part, I think we're very excited because of the complexity, how predictive it could be. And now we're seeing that it actually is very robust and it works for a wide range of compounds. So we're very excited in that, and I hope that the community pays attention to those methods and it starts adapting more of the iron chemistry, because to me that there's it's actually one reaction that industry can quickly just pick up and use in their labs right away, and it's very predictable.
We hope you're enjoying this episode of Bringing Chemistry to Life. Stay tuned at the end of the episode for information on how to access content recommendations from our guest, as well as information on how to register for a free Bringing Chemistry to Life t-shirt. And now, back to our conversation. You mentioned the excitement about understanding the mechanistic aspects of the reaction. I know it's difficult on an audio format without any visual help. Can you describe the mechanism a little bit?
Yeah, in this mechanism, what we think is going on, you have the pre-catalyst. That's a thing that you buy from a company. You reduce this one to you change the oxidation state to make the active catalyst. We're learning more about that. What is the nature of that active catalyst? What is complicated about iron is that you have to worry not only about the coordination, not only about the oxidation, but also the spin state. So you have multiple different parameters that we need to explore computationally and experimentally as well. So how do we determine all those things? And from there, what we think is what's going on is that this active catalyst, the first step that it does is just rips apart a carbon halogen bond. So it just grabs, so it's very selective for carbon halogen bonds. And we have a ranking of what follows, so which one's faster, which one's slower. So it rips apart the carbon hydrogen bond, it generates a radical. And now the key thing is to control whether the radical rebounds to the iron or does the radical dissociates from the solvent cage and reacts with something else, undergoes a radical cascade transformation. And there's multiple radical cascades in organic chemistry. So we're thinking, why can't we just couple both? A radical cascade with iron chemistry. So let's have this radical dissociate from the solvent cage. That's what we want. Undergo a radical cascade while somehow tune this iron to still remain active. And that after the end product of the radical cascade, now that's the one that rebounds to the iron and undergoes the selective final carbon-carbon bond formation. And we're able to show that. So we're able to couple a cross-coupling cycle and a radical cascade cycle together. And I think that's what we think is the mechanism. We're collaborating with other spectroscopists, inorganic spectroscopists right now, to understand what is the really identity of that iron species. Because I think if we're able to understand that identity of the iron species and understand what are the factors that control the lifetime of this species, then we're able to span basically the radical cascades to longer, more complex radical, systems, and not just this kind of simple systems that we have right now. So understanding the lifetime of those is going to become crucial down the road. And the only way that we're going to achieve that is through mechanistic understanding, because you're not going to get an idea of a lifetime by simply trial and error in these reactions, because all reactions are done within 1 hour. So you have the kinetics experiments become very challenging to do. And detecting this intermediate becomes challenging. Detecting whether the oxidation spin state becomes too complex, that you really have to go beyond our expertise. And now we're excited about that other part. Maybe now we're starting integrating more spectroscopy experiments in our chemistry. I'm learning about those, but I'm not afraid of going into those and saying the next 5 years of my life, I think I'm going to spend more learning about spectroscopy. So now in our move to Texas A&M, it was clear that will be one of the focuses that I want to go to. It's like, we need all these resources. We need more spectroscopy methods, because I really care about this identity of this highly reactive species. And if we understand that, then those principles could be applicable to a wide range of different reactions, not just the ones that we're studying.
So these iron systems are going to become your main line of research going forward, probably then.
Yes, I think that's going to be the main line of research, but on the synthetic side. But we, of course, in the computational side, we have many different directions that we're tackling that we're super excited about all those directions.
And the beauty is that you can collaborate with, a lot of different groups to combine the experimental and the computational parts together.
Exactly. And a lot of times we just interested, we see a paper that grabs our attention. The student's really excited, they do all the computations. And I told them, we're going to contact the person that wrote this paper and say if they want to collaborate. If they don't, then we do all the validations in-house. So in a way, we're always seek for experimental validation. And I think the advantage that we have is that oftentimes maybe the collaborators, like, I already went through that area of research, I'm not as interested anymore. And for us, well, we're going to do the experiments ourselves. And we go into the lab and do those experiments to validate because we have the resources. And I think we're getting the expertise on those areas that we go and validate. And I think the community in general will benefit more.
Yeah, these types of reactions are really, really interesting. I mean, I've read a few very interesting pieces of work on people very often combining photocatalysis and nickel catalysis, right, to generate the radical and then sort of confer specificity to the reaction, which is kind of counterintuitive in my mind, because once you generate a radical, you have a highly reactive species in your mixture, and controlling it will potentially be a nightmare. But we discussed with Kathleen Biggins in a just a few weeks ago, just in interviewing her for the podcast, and these types of radical couplings are even used in DNA on DNA tagged molecules. So you have an extremely multifunctional molecules there, and yet you still have specificity in the reaction. It's surprising. It's amazing. And I know you've worked on something kind of similar, right? On this sort of geocatalyst systems as well.
Yes. So I guess what's kind of different with our iron system, we also collaborate with a lot of experimentals, Gary Molander, Don Watson, Tom Brown, a lot of the people, the leaders of the field working on nickel catalysis, where they combine the radicals. And I think in that case, what they're taking advantage is of slowly generating these radicals. And therefore, you have a low concentration of these radicals. Now you take advantage of basically a smaller concentration and how this is going to affect the reactivity. Well, we take advantage of not only slow generation of the radicals, but also the extremely fast kinetics of the final step, or the cross-coupling step. So that's oftentimes the main differentiating factor between these two types of chemistry, and both could be widely applicable to different things. Sometimes you don't want a reaction to happen so fast. Sometimes you want the reaction to slowly progress and not be as fast as the ones with iron. But they both have advantage. But it's kind of surprising to me that as I was an undergraduate learning about radical chemistry, every time you see radicals, it was almost like carbocations. Like, those are great species for mechanisms, but not something that are applicable to really designing new systems or new materials and whatnot. Is like, most likely they won't be as applicable. There's some applications, but they're not as accepted. They always think if they're highly reactive species, and controlling those highly reactive species could be a nightmare, right? We introduced that right away in organic chemistry when we introduced radical chemistry. In halogenations, like, this is going to be a nightmare of we have some predicting reactivity, but you're always going to get a nightmare of different products, and selectivity is going to be an issue. But now it's kind of amazing where the field is going where it has been in the last 10 years in terms of combining multiple ways to generate radicals and controlling radicals.
Yeah, it's in my opinion one of the most exciting area of innovation in mechanistic chemistry, really. And some people have the perception that there isn't much innovation in chemistry anymore, but this is a brilliant example of why that is not true, right?
Yeah, it's not only a brilliant example that it's not true, but I think it also is a great training for changing the mentality of students. Like I said, now it's changing the mindset that radicals, this highly reactive species, what we thought of highly reactive, now we are able to control them. And that goes long ways, right? It goes long ways, like, in terms of, let's say, for me, I can relate it to more general area that having a African-American president, now it inspires a lot of people saying, I could do that. So now in terms of organic chemistry, this radical chemistry showing that these radicals that we thought that were not going to be as selective, that nobody will really do anything practical, they have limited applications. Now we have shown that a lot of people working in this area that you could control these radicals. And that changes your mindset. It's like, why can't we go to those other reactive species that we thought, carbenes, carbocations, and so on and so forth? And now we should be able to control those, because we have shown that for radical chemistry, we could do that. So now it opens up a lot of space where we could go. It's like, there's no reactive intermediate anymore that we cannot control. And I think that could change. It's just about, do you have the energy to go and try to control those intermediates. But I think now it kind of inspire a lot of new generations like, wait a minute, if they could do that with radical chemistry, we could do that with any other reactive, highly reactive species now.
Do you think organic synthesis will look different 10 years from now?
I think so. I think organic synthesis is going to look very different than what it is now, because I think it's going to be, you have to be more conscious about why exactly you're trying to make this product. And the tools are going to be more. So identifying how you use those tools and why you're using those tools, I think ultimately is going to come down to not just a novelty, that's maybe for a publication, but in practical sense, like, you really have to worry about the cost of these compounds, right? The catalyst. And there's going to be, if you have multiple ways and now you're able to decide, wait a minute, this reaction doesn't work, but I want to use this particular catalyst. Can we make it work? Can we make this catalyst? And I think in 10 years, computational chemistry is going to be a dominant force, whether it's machine learning, whether there's transition state calculation and so on, where now they're going to become very practical, where it's going to become between a choice between, if I order this chemical, it's going to arrive in a week, versus I could easily go and do all these computations, and maybe that will say, you should not order this chemical, order this other one instead, because this is the one that it would be more useful. So I think we're going to become more selective in terms of designing chemical, basically, systems. So I have a feeling that computational chemistry is here to stay in the long run. I think we're always seeing a lot of productive results coming in that area, and it could only get stronger. So it's not something that it's going to fade anytime soon. So the faster that we implement computational modeling in our undergraduate curriculum, expose students to some of those aspects, the better we're going to be.
And it has to be this new, more modern type of computational chemistry, right? Not an elitist group of chemists who are just fighting for a fraction of an angle in a chemical bond, or right? It is someone who is actually looking at the practical application and what the fundamental understanding you get from the means for the actual organic synthesis that lives in the real world.
Exactly. I think with all the given approximations, I mean, whenever I give a seminar, you always have people from the very theoreticians, and they say, well, this method has been shown to have several different drawbacks, but at the same time, we're trying to build a model which ultimately our goal is really can we able to capture, given the complexity that goes in a chemical system, even with two different reagents only, how complex it really is, with the solvent, how complex it is. Take that very complex system, get a working model that then we could use to predict new things and not get lost in the little details. So do you really have 3 molecules surrounding this core? Do you have 4 molecules? Or what is the lifetime? What is the equilibrium? It's like, we're not going to get into those details. I think we could get lost in those details, and there's a lot of people their fascination to understand that equilibrium and whatnot. But for us, we cannot get lost in those details. We're able to live by a certain aspect, a certain uncertainty, a certain error, as long as we're able to design an experiment. And then we do invalidate, and we go back and we work in that loop. But we have to be okay with saying, we're okay if this barrier is not as predicted as with experiment, as long as we're able to design the next one that is going to be faster or slower. And that's all we care about. We care about trends, making things faster, making things slower, making things more selective, less selective, not necessarily by a huge amount and so on, and not necessarily understanding all the intricacies and things that go on, because we understand that, we also know that the chemical system is very complex and there's many different things that go on. I mean, we could get lost in understanding the phases of water, and that's been studied for years and years, and understanding all the different phases and conformations, and we could get lost.
Yeah, a very pragmatic, Osvaldo, and impactful way of looking at it, and that's what I believe more and more groups should focus on, and we have seen actually more group following suit, and in many ways your team is leading the way. Obviously, you've made the most out of your personal and professional path so far, and you have achieved a lot, and you have a bright future in front of you. But you're also getting involved with trying and help other people who, like you, might face some hurdles, right, in getting some deserved success in their career. And so can you talk a little bit about your involvement in initiatives to facilitate access to STEM education?
Yeah. So I'm approaching this issue as in a holistic way. So one thing that I'm very involved is I'm part of the Alliance for Diversity in Science and Engineering, ADSI, where we build chapters all over the United States, and it's a graduate student-run organization with the aim of targeting community college students like myself that I was. And the reason why we're targeting community college students is because in those community college, actually you don't have underrepresentation of people of color. Sometimes they're overrepresented, but we lose them. We lose a lot of those students as they go into the 4 years, so they're not transferring. So why not target those already college students? And then if we're able to get the majority of them to transfer to 4-year universities, we might be able to increase the number of underrepresented minorities in the sciences. So I'm heavily involved in that. I established one at the University of Pennsylvania as a postdoc, and I established one in Maryland. Now I'm helping other universities establish similar programs because it's been very successful. In addition, now I have the opportunity to write grants and propose fun things like, I think I want to have 3 students this summer. It takes me a day to write this proposal and whatnot. But I think the community is very accepting towards providing opportunities, and usually gets funded. And I bring 2 or 3 community college students from underrepresented backgrounds in my lab. They're exposed to the chemical environment as I was. And then we're more involved in providing mentorship, basically advice moving forward. And they actually see that you could get paid to do this cool stuff, right? If they're fascinated about science, be like, you could be here all day. We have all these chemicals. There's so much unknowns that you could create an impact. And if you're able to develop a method, it might be the cure for cancer. It might be the cure for different diseases. So it can be very impactful. You have to be able, and as long as we're able to communicate that to students, like, this is not just theoretical work that is never going to be practical. I think we're developing things that eventually somebody could use to make the next molecule that could help in different ways. And we're doing a lot of the initiatives in that. And I also participate every opportunity that I have to speak to students, high school students, and community college students. I take that opportunity because I was looking for those. I was growing up. I think having somebody that is there, that is approachable, that tells you about what could be one strategy, and connecting with other people, I think that becomes very important. So I think we should be doing our job in providing those, and rather than waiting for those students to come and reach to us, we should be really be doing our part and reaching to them, and we'll kind of find a common ground eventually.
That is absolutely great. Congratulations and thanks for all your work. This is really going to make a difference for a lot of people, and that I'm sure makes you proud. There is one final question I always like to ask for closing our interviews, and there's no better person than you to ask it. It's what's one piece of advice you would pass on to a young scientist or students just starting in their own career based on your own experience?
I think one of them is to own your identity, whatever you are. Don't try to follow the same paths that other people follow. If you want to become a professor, if you want to become a scientist, if you want to become a politician, whatever you want, don't follow the path that somebody already has taken to get there. Don't be afraid of owning your own path or your own background, those experiences, because that's going to make you unique. Then don't be afraid of, maybe this is the wrong step. I got a lot of criticism as I was making my moves, whether that was the best move, whether that was the best school, that was the best PI, and so on. It's like, but as long as you own that and you own that, you're going to become very unique, and therefore you're going to have a unique perspective. You might change the way we do science. So I actually say, don't follow any pathway. Just follow your own pathway, create your own pathway. And as long as you have a goal of where you want to be, I think you're going to be okay.
That was Dr. Osvaldo Gutierrez, Assistant Professor of Chemistry at the University of Maryland, and one of the Chemical and Engineering News' Talented 12. Thanks for joining us for the start of Season 2 of Bringing Chemistry to Life, and keep an ear out for more. If you enjoyed this conversation, you're sure to enjoy Dr. Gutierrez's book, video, podcast, and other content recommendations. Visit thermofisher.com/bctl to access these recommendations and register for a free Bringing Chemistry to Life t-shirt. You will find the link in the episode notes on your app or browser. This episode was produced by Matt Ferris, Matthew Stock, and Emma Jean Weinstein.